Hello, everybody. I'm meteorologist Sean Sublett, and welcome to Across the Sky, our national Lee Enterprises weather podcast. Lee Enterprises has print and digital news operations in 77 locations across the country, including my home base here in Richmond, Virginia. I'm here with my meteorology co-host from Across the Sky, Kirsten Lang in Tulsa, Matt Hollander in Chicago, and normally we have our pal Joe Martucci joining us from Atlantic City, but he's on leave, as it were, right now, down in sunny Orlando, Florida. Matt, Kirsten, how are things there? Let's start with you, Kirsten. How are things in Oklahoma?
Man, it's just been a roller coaster ride of temperatures here. We've had 70, I guess we got 70 on Tuesday, and then we woke up Wednesday morning, it was 24. And today it's about 55. We'll hit upper 60s, and then we're back down, in the 20s over the weekend for overnight lows. So just kind of all over the place that time of year, change of seasons. But aside from that, we're living up to the song from Oklahoma where the wind comes sweeping down the plains, because we're getting gusts up to about 30, 35 miles an hour at times. So just, windy fall for us here.
Matt, how are things in Chicago, buddy?
A lot colder than where Joe is in Florida, I can tell you that. Even though we're getting it's kind of the same thing here where it's been a little bit of up and down, though everything just colder than what they're seeing in Tulsa. We're going to get another little warm up right before, unfortunately, the weekend, and then a cold front comes and goes right back to the cold for the weekend. But what I am excited about seeing is, though it's going to be staying pretty cold, it looks like after this next front, it's going to be more consistent. It looks pretty dry, which I'm okay with. That means we don't have to talk about figuring out if it's going to be sleet or freezing rain or snow. So, cold, unfortunately, that's going to happen. But if it's dry, I can deal with the cold.
Yeah, it's funny because here in Virginia, when it gets really cold, people are like, well, if it's cold, why can't it snow? We're like, well, I wish it were that easy, but it just isn't that easy. But yeah, the transition is underway. It's the first day. We're recording this on December 1st, the first day of meteorological winter. But it also means it's the end of hurricane season. And I think most people are happy that a lot of the initial outlooks were that it would be a little busier than average. But when we look back, it's actually close to average, or it ended up being a little less active than average. Nonetheless, as we always say, it only takes one bad storm to make for a bad season. And of course, Ian, I think, will go on the history books as that storm. But with that in mind, I want to bring in our guest this week, Tyler Winkler. He's an oceanographer at Woods Hole Oceanographic Institute in coastal New England. His research examines the structure of sand and mud found on the ocean floor. And that can help us decode changes in ancient hurricane activity in the North Atlantic. Now, his most recent research sheds light onto how active hurricane seasons were in the distant past in the North Atlantic. He's a Texas A&M Aggie, earning his PhD in oceanography and his bachelor's in marine biology from there. Tyler, thank you very much for joining us on Across the Sky.
Yeah, thank you so much for having me.
So I read a little bit of your work, and I really want to get into this pretty deeply as possible for general audiences. But first off, how did you get involved in this type of research, which from the outside really seems kind of like a niche?
Yeah, absolutely. So I started out in marine biology, and I was actually examining underwater ecosystems in flooded caves in Mexico, and looking at little cave adapted shrimp and things and how they existed and how they sourced off of food. But it got me thinking about how sensitive these really delicate ecosystems are to things like storm surge and intense hurricanes coming in that can actually cause those caves and that aquifer to flush out and really cause a lot of damage. So I started thinking about, well, how can we think about how these storms are changing over longer timescales and how threatened are these ecosystems? And so that's where I actually connected with a geologist who became my PhD advisor. And we started looking at these distinct storm layers in sediment records that can be found in caves and in sinkholes and in coastal ponds all across the North Atlantic. And we can actually then date those individual storm layers to get a better idea of when and where these storms were occurring in the past, and whether or not that's changed in response to things like climate variability over longer timescales. So it really kind of just started out thinking about ecosystem sensitivity and protecting the environment, and then it kind of grew into developing these near annual records of storm activity from these distinct locations throughout the Atlantic. And that's really been very informative to us about not only how hurricane activity can respond to longer term climate variability, talking about thousands of years of variability, but also really assessing regional risk. So what shorelines are most at risk to repeated storm activity over time? And so I think that's where what kind of motivates me for a lot of my research is I'm really interested in thinking about what shorelines are most at risk and how can we focus on making those shorelines more resilient to future hurricane activity.
That's really amazing stuff. And my understanding of paleo reconstructions is rudimentary at best. So can you give a brief explanation as to how we can use these types of sediments to make such conclusions? I think to a lot of people who maybe don't even live near the ocean, they're like, how in the world can you go down and look at the mud and tell me what the hurricane season was like 300 years ago? Can you give, a relatively straightforward explanation as to how these correlations are made?
Yeah, definitely. So the first thing that it comes down to is finding a site that's going to record kind of undisturbed sediment records. So obviously, whenever a hurricane's coming through, it can actually cause lots of erosion and wash away sediments. So taking a core just from a beach isn't going to actually do that. That's actually sediment that's been reworked and washed away by storms over time. But what we actually look for are these offshore sinkholes called blue holes. And essentially, they are just like large tubular sediment traps on the ocean floor. And all of that sediment that's being washed over actually gets deposited into this natural sediment trap. And what that starts doing is start layering itself, kind of like a layer cake over time. So we start seeing during non-hurricane years, we see very, very fine grained sediments like mud being deposited into these blue holes. But whenever a hurricane washes over, it's transporting larger coarse sands and gravels and lots of different organic matter and debris. And that's forming a distinct layer on top of those mud layers. And so over through time, it's almost like a barcode or like a layer cake of these distinct storm layers versus natural background sedimentation. So what we can actually do is look at the size of those grains. We can look at the chemical signature of those distinct coarse sediment beds. We can also look at the different types of microorganisms that are living inside of those little layers. And they're very, very distinct in storm years versus non-storm years. And so what we can actually do is we can actually date material like leaves and sticks and oyster shells that are found in those layers. And that can actually, using radiocarbon dating, which is a type of geochemical technique. And based on that, we can determine when that storm occurred. So what we're doing is we're developing these layer cake reconstructions from different sites all throughout the North Atlantic so that we can form both regional compilations of these records that give us a good idea of the regional picture of what's happening with long-term hurricane frequency. But we also then develop them in other regions as well so that we can start to piece together piece by piece what's happening across the North Atlantic, because each region in the North Atlantic has very distinct hurricane histories. For instance, the Bahamas is much more active generally throughout the past than what we are seeing at times in New England. And there's a lot of different things that kind of factor into that. But what's really important is that we're creating this network that kind of gives us this broader insight into this.
Hey, Tyler, it's Matt. With these core samples, and I know you're sampling them from many different locations, how far back do they go, and does it vary based on the location?
Absolutely, yeah. So it does vary based on the location. So every site has its own distinct sedimentation rate. So areas in the Bahamas tend to actually have a lot higher sedimentation rate than areas, for instance, in New England. And that really just has to do with how sediment's being produced in these environments. So that's one thing that factors into that. So typically, whenever we have very high sedimentation rates, the records that we're capturing tend to be shorter records temporally. So that's stretching usually in the approximately 2,000 year long kind of records. But they're nice because each inch of sediment represents just a few years of time. So we can really get a distinct window. So having those high sedimentation rates is actually very good for those. So some about 2,000 years long. A lot of sites, though, in the northern higher latitudes in the North Atlantic, like in New England, actually have lower sedimentation rates. And those can span up to 8,000 years in the past for some of them, and even more in some sites. But typically, if you want to have the nice yearly snapshot, you're looking at anywhere from 8,000 to 2,000 year kind of long records are kind of what's ideal for that. And so it does kind of just depend on the region for that. So yeah, that's kind of how some of those different sites are variable.
Tyler, can you tell us a little bit too about what these blue holes have told us, or told you, I guess, about hurricanes in the past?
Absolutely. So what we're learning from these blue holes is that, so if we look at the last 170 years, which is whenever we have instrumentally observed hurricanes in the North Atlantic, the Bahamas overall stands out as a pretty active region for hurricane activity in the North Atlantic. And that's because a lot of the storms that form in what we call the main development region off the western coast of Africa tend to go on and impact the Bahamas, but Bahamas are also being impacted by storms that are forming in the Gulf of Mexico and the Southern Caribbean. So they're kind of this focal point where a lot of North Atlantic hurricane tracks pass over the Bahamas. But what we're learning is that there's actually times in the past, such as from around 1300 to about 1800, where the Bahamas was actually being impacted by more hurricanes than it is today. So there's even greater threat potential for hurricane frequency at times in the past. Now, what's to be distinguished about this, what we're seeing as Earth's climate is continuing to warm is that we're seeing more frequent intense hurricanes. So hurricanes are getting stronger and we're seeing more of those frequent and most intense storms. But what there is in the past, our blue holes are telling us that the overall susceptibility and frequency rate of being impacted by sometimes weaker storms can be higher. And so it's actually very difficult to understand the relationship of climate and overall hurricane frequency over time, because there's a lot of different factors that can impact where these storms are being pushed to and what kind of impacts they're having on that environment. But what we're seeing with these blue holes is it's telling us is that even within the natural climate system, before we started to warm things up and produce more intense storms, there is a greater regional threat for just being impacted by some number of storms. And that's pretty important to think about, because as we're looking at projections of sea level rise over the next 100 years, there's up to about a meter or about a yard of sea level that's expected to rise over the next 100 years. And that would actually cause the Bahamas to lose about 13% of their total land area. Now, that means that a lot of the areas that were most completely inundated and flooded by Hurricane Dorian, which is category 5 hurricane in 2019, those areas that were underwater during that storm will already be underwater just due to sea level rise over the next century. So any increase in the frequency of storms over the next 100 years, even those weaker storms could produce more intense flooding than Dorian. So that's a real problem. And so that's why trying to actually understand the long-term susceptibility and risk at these certain regions to storm activity really helps us to improve the estimates of risk so that we can, okay, these are shorelines that we have identified now as we really need to think about coastal resiliency and how we adapt to things like more intense frequent hurricanes and increased sea level rise over the next century.
Well, Tyler, with that in mind, let me ask you this. I don't even know if this is something you've been able to do yet, or if it's one of those things for further research. But we know that in more recent times, let's say 40, 50 years, we've got satellite records of hurricanes. Then you've got ships logs and things like that going back into the early 20th century, into the 19th century. Is there any way to do some type of correlation with your sediment data with some of this other data in terms of ships logs, satellite data, anything like that? Is there any way to kind of connect those dots to help with verification?
Yeah, no, that's a great question. And so that's actually one of the things that we're starting to do with our papers, especially as we're developing these. We call them higher resolution. So whenever we have these high sedimentation rate sites with these great snapshots, we're actually cross-correlating them with these other records, these satellite records, with these instrumental records, with these historical records, and really trying to make sure that what we're documenting in these paleo sediment reconstructions is lining up with what we're seeing in these other records, at least over that small overlapping window, just to make sure that the story that we're telling is accurately reflecting hurricane activity during the time that we know. So it's essentially calibrating the records to this data that we do have and that we can trust, and then extending that back in time. And what we're seeing is that, especially with these records in the Bahamas, we've been very, very effective at lining up known hurricane activity during the satellite period and during the last 170 years of instrumental weather data to these storm records. So they're very, very accurately reflecting this. And so that way we can be more confident that what we're extending back 2,000 years into the past is actually reflective of what's happening regionally with hurricane activity.
And Tyler, when you're looking at these core samples, are you able to determine the strength of these hurricanes? Have you developed a method where you can determine even the category of the hurricane when you're looking back in the past? Or is that something that once you get too far back, you can tell there was a storm, but there's no way to actually determine the intensity of it? Or is it actually quite easy to do no matter how long ago it was?
So that is one of the challenge with these records. So there are ways to be able to identify local intensity of the storm. And so what I mean by that is there's a lot of different factors that can control how intense a storm is presenting itself at a very local level. So you can have a category 2 hurricane that directly impacts a site that's being hit by the eye wall of that storm over an extended period of time. Let's say it's a very slow moving hurricane, and that can actually produce larger waves than a hurricane that is a category 5 strength that passes much further away on a weaker side of the storm. So what we can kind of interpret from that, so oftentimes stronger storms will result in thicker sand deposits and coarser sand deposits. So there will be larger chunks of debris. There will be more of it in storms that are locally more intense. So by looking at the overall coarseness of the deposit and the thickness of it, we can start to get an idea of how strong that storm was locally. But there is some difficulty being confident about the overall characteristics of the storm. Was it a strong storm that passed further away? Was it a weaker storm that made direct impact? So that's kind of where we do have some ambiguity in the records.
Tyler, that's really, really cool. And I want to talk a little bit more about that after the break in terms of what kind of sediments and locations that we're seeing those things. So we're going to come right back after a brief break, talking with oceanographer Tyler Winkler from Woods Hole Oceanographic Institution on our Across the Sky podcast. Stay with us. We're right back. And welcome back to the Across the Sky podcast. I'm here with Tyler Winkler and the rest of our team from Lee Enterprises, talking about paleo reconstructions of hurricanes. In other words, looking at data from the ocean floor and telling us how active hurricane seasons have been in the North Atlantic in the distant past. Tyler, back to the point we were talking about earlier, how we look at mud and sediment in different ways. We date these samples using radiometrical dating to figure out how things have decayed and figuring out how old they are. But how do you go access these samples? Are you diving? Are you doing it just from the shore? How is this done? Because I'm trying to imagine what it's like going into the ocean, diving into the ocean, finding a cave with some equipment and acquiring a core sample. So could you just walk through that a little bit, the actual process of doing a little field experiment like this?
Yeah, absolutely. So the first thing that we do is we actually sit down on the computer and look at Google Earth satellite imagery and try to identify these blue hole circular features either offshore or sinkholes just onshore, or we talk to local people that live in these areas that we work and try to figure out where some of these caves might be. And then we kind of go and we'll actually explore the site using a few different things. We'll actually do some mapping and surveys that can tell us how much sediment has actually accumulated in the site, because we're looking for sites that are obviously accumulating a lot of mud over time. And then once we've actually picked a good site that seems to have a lot of sediment, we'll actually go out, and there's a few different ways that we can collect these cores. So sometimes we'll actually go down on scuba and in the water, and we'll kind of actually just take a cylinder core barrel. It looks like a very large straw, and shove it down into the mud and hit it with the scuba tank to actually drive it down deep. And then we can use suction to actually pull it up out of the mud. And then that's how we take that back. But we can usually only get shorter cores with that, talking, approximately 8 feet long to 10 feet long. Other ways that we can do this, though, is that whenever we're working in really remote locations, like some areas in the Bahamas, we'll actually take inflatable boats, and we will either go out on an airboat to get to these remote locations, or we'll just have to kind of pack it through along the shorelines to get out to these blue holes, and then we'll actually blow up these boats. And then from there, we can actually set up a kind of almost like a crane mechanism where we can lower down a coring device that actually is attached to one of these straw-like tubes that vibrates it down into the mud so that we can get much longer records. These are records that are up to 60 feet long. So that's one way that we can do that. The easiest way to do it, though, is to get on a very large research vessel like the RV Atlantis that we have up at Woods Hole, and to actually go and collect these cores off the back A-frame of that boat. And so we can use this fiber coring technique that I mentioned, where we shake the pipe down into the earth, or we can actually use what's called jumbo piston coring, which is where we have a 5,000-pound weight attached to essentially a piston that we drop down into the ocean, and it actually sucks the mud up into the tube. So there's a lot of different ways that we can do that. But once we actually have these tubes collected, we'll take them back to the lab, and we do a lot of different analyses on them. So we'll do things like running them through X-ray or CT scanners, some similar like what you use at the hospital. But that actually lets us see density changes down the core, and we can actually correlate that with the different types of storm layers versus non-storm layers that we have in the sediment record. And then what we'll actually do is we'll open these cores up. So we'll split them using electric shears, and we can actually then see a nice picture of what this layer cake of sediment looks like. And so we'll take lots of high resolution pictures so that we can go back and look at that. But we'll also go through and we'll quantify and measure changes in grain size down the core. We can also use elemental scanners to look at changes in the elements of the sediment down the core. And that can actually correspond to and tell us whether or not the sediment is being sourced from the land or parts of the deeper ocean, or if it's coming from estuaries or coastlines. So that helps us to determine where sediment being deposited into these is coming from. And that lets us know whether or not it's, the storm washing it in from the marine side, or if this is outflow runoff coming away from the storm after the storm. And so that's one of the things that we kind of look at. And then we actually go and pick out the individual things that we want to date so that we can create our age model so that we know how old the sediment is, and we can actually put a time on when this storm occurred in the past.
I'm trying to wrap my mind around a 60-foot core and going through all of that information. And so what I'm curious about is how much does a length of a core correspond to how much time? So like when you're talking about just doing it by hand and getting an 8 and 10-foot core, how far back are you going? How much distance are we talking about within those cores for how many years are represented?
Absolutely. So that can really just depend on how fast sediment's being deposited into that site. So sometimes one of those 10-foot long cores will represent 8,000 years of time. Other times, depending on the site, if it has a lot of sediment being dumped in very quickly, that same 10-foot core may only represent 100 years of time. So it can really, really vary. So especially the sites that are offshore and in the coastal zone, those tend to have higher sediment rates. But sites that are coming from further inland, like inland sinkholes, those tend to have lower sedimentation rates. So a lot of times those will be lower. But for instance, like that 60-foot long core that we took, that only represents about 1,500 years at one of the sites. So it's meaning that, we're depositing about a half an inch of sediment per year over this 1,500-year long period. So that's why these sites can be really, really good for understanding year-to-year changes in hurricane activity.
Tyler, just to, again, kind of paint this picture for our listeners, can you kind of give us a little bit of I guess, background on how long this process would take for you and your team, and how many people are out there with you when you do that? But, just from start to finish, so you find a blue hole, you pull this core sample out, you go through the process. How long does that usually take for you guys?
Absolutely. So like I say, the first thing is kind of just sitting in the computer, picking where we want to go. And that, can be done over the course of planning the project. We put a couple months into that, but we usually actually kind of tackle these bigger field trips, usually about a month long at a time. So there'll be 5 to 6 of us going out to the field, and, each person on the boat or on the coring raft kind of has their specific task. And we kind of get really into a rhythm, and we can end up collecting multiple cores from lots of different sites. And then, so that's about a month actually getting all of that and getting it brought back. And then once we have it back in the lab, that's really where the long part starts. So just getting the core split open and analyzed and kind of all of that can take anywhere from 2 to 3 years just to get all of that data. Because if you think about it, we're sampling, every centimeter of each of these cores. And so for those 60-foot long cores, for instance, that can take quite a long time to kind of get through that and do all of these different analyses. But then once we have all of that data, we actually then have to go and interpret it and figure out what that means. And so that can take quite a long while in itself, because we want to make sure that we're getting our interpretations right. We want to make sure that we're taking the time to calibrate it to the known hurricane records from satellite data and historical observations to make sure that our records are actually reflecting hurricane activity and not something else. So that's something that we take a lot of time to make sure of, because, we want to make sure that as we're kind of building and compiling all of these records to kind of form these regional signals, we want to make sure that each piece of the puzzle is telling us an accurate reflection of the story. Start to finish, on average, I'd say that developing one reconstruction from one area could take anywhere from 3 to 5 years.
So Tyler, you said a lot of what you've done or what you've seen is around and near the Bahamas, which kind of makes sense from a meteorological standpoint as well. Aside from the area around the Bahamas, where else have you pulled samples, and are there any other places in the Atlantic Basin, and we mean the Gulf of Mexico, Caribbean, and the rest of the Atlantic? Have you seen some signals, if at all?
So my group and my colleagues and I, we have sites that we've been working on from the Yucatan Peninsula in Mexico. We also have sites from all along the western Gulf of Mexico shoreline of Florida. And then we also have, so even we're actually about to go sample some of the areas impacted by Hurricane Ian just this year to kind of do some work there. But we also have reconstructions all up along the northern East Coast. So in New England, one of my colleagues, Jeff Donnelly, has done a lot of work up here actually looking at these sediment records that accumulate in glacial ponds. So ponds formed during the last glacial period, kind of all this ice carving out these features in the landscape. So a lot of times that's where a lot of this work has been done, and where a lot of this work started actually was up in New England, looking at storm changes up there. And then I actually also have projects all the way up in Newfoundland in Canada. So looking at kind of the tail end post-tropical transition of some of these hurricanes and how that's translated up at higher latitudes. So that's some of the areas that we're working in. And what we are seeing is that each kind of region that we're kind of looking at does have its distinct signals. And a lot of it has to do with where we hypothesize it has to do with where the storms are forming. So at times in the past, when we're seeing elevated activity in the Bahamas, sometimes we're also seeing at the same time elevated activity in parts of New England, because a lot of those storms that are impacting the Bahamas are then kind of recurving and going up along the eastern U.S. shoreline. So there's sometimes highs there and sometimes there's not. And what that means is there a lot of times, as in the past, for instance, changes in atmospheric pressure gradients that are kind of causing those storms to get pushed further south or straight forward into the Gulf of Mexico or into the Southern Caribbean. And there are also times whenever storms are forming more in the Southern Caribbean or in the Gulf of Mexico. And so obviously the Bahamas are still being impacted by some of those storms, but we're seeing much higher activity in the Yucatan Peninsula and the Gulf of Mexico, whereas we'll often see lower activity in New England during those times, because those storms that form in the Gulf just tend to not usually over longer timescales impact New England as much. So we definitely are seeing some regional variation and patterns that are starting to emerge over longer timescales as we develop more and more records from different regions in the Atlantic.
All right. Well, then with that in mind, and I want to be sure I understand what some of the take-home messages here are, that there is evidence, and stop me, please, Tyler, stop me if I'm going in the wrong direction. But there is evidence coming to light that in this let's say pre-colonial area, let's say 1300 to 1700, there's evidence suggesting the North Atlantic might be busier, had been busier than in these last couple of 100 to 300 years. Is that what some of the data are at least suggesting? I'm not saying that's cemented, as it were, but is there some evidence for that?
Yeah, there's some evidence for that. And what that really is kind of telling us is that overall hurricane frequency and where it's going and how that's impacting certain regions, that can be hard to predict because there's a lot of very, very short-lived weather patterns and variables that can cause one storm to go one place and not another. And it can almost appear random. It's not random, but it can almost appear that way. So, but what we're seeing is that there could be a lot of variability in weaker storms over longer timescales. And what we've actually seen over the last 170 years is that a lot of areas in the North Atlantic are actually at prehistoric lows. So some of the lowest levels that we've seen over the last 2,000 years. So what that's really telling us is that given that it's hard to predict the frequency of hurricanes, what we're seeing based on these paleo records is that regional risk may actually be much higher than what we're anticipating for certain regions in the North Atlantic. And so but what we do have a confident grasp on is that storms are going to be continuing to get more intense and going to continue to have increased rainfall potential due to climate warming. There's just more moisture available. Moisture and warm moisture fuels storms. So with all of that, storms are going to be stronger, and there's expected to be more of those strong storms. given that we're at a historic low in frequency and given those expected projections of how storms will change in the future, it does certainly mean that certain shorelines are going to be at increased risk than what we previously expected.
Yeah, that's probably not a surprise considering how much development there's been along the shorelines, especially here in North America. When we talk about how this is kind of at a relative lull, before or compared to pre-colonial times. Is there a way to quantify that? Is there a way to say like, oh, you know what? It seems like it might have been about 50% busier back then, or twice as busy. And I know there are statistical things that go along with that, so it's not perfect. But is there any kind of order of magnitude when you see the data that you're seeing to help quantify how much busier it was 300 to 800 years ago compared to more recent times?
Yeah, absolutely. So, for instance, in the Bahamas, where we currently have kind of the most data and the most kind of confidence in some of these, we can actually see that. So while we typically always record compared to, so for instance, we know how many storms have impacted the Bahamas over the last 170 years. When we kind of calibrate our record, we know that we are under recording. And that's just because not every storm that passes is necessarily going to leave a layer. But we are reflecting the trends very, very accurately. There's a very high correlation in the trends. So what we can do is if we kind of extrapolate the rates that we've seen in the Bahamas now compared to what it is at that time, and then look at the relative increase in hurricane frequency, for instance, 400 years ago, we can actually see that hurricanes were about 80% higher in the Bahamas region about 400 years ago than what we've seen over the last 200 years or so. So there's definitely, I mean, an 80% increase. That's almost twice as many storms per century as what we've observed. And so that's something that, that particular region, and really there's no region in the North Atlantic that's prepared to deal with the threat of almost twice as many hurricanes per century compared to what we've observed. We think it's bad now, but it can be worse.
Yeah, it's crazy to wrap your mind about that, to think how many more storms that would be and the impacts now that there's so many more people instead of hundreds and hundreds of years ago when the population was much smaller and there wasn't the infrastructure that we have now. It's kind of a scary thought to think that what if that was to happen again? I think the other takeaway here is this is a great evidence that it's not all about sea surface temperatures, because we're talking about times when the Atlantic was not as warm as it is now due to climate change. But it just shows you how complicated it is. There's so many other factors that go into hurricane formation, particularly the frequency of the storms, how much wind shear there is, how much dry air there is over the Atlantic, how many waves are coming off of Africa. And so I'm wondering about kind of your next steps. Is there any way that we can kind of try and figure out why there were so many more storms? If that's the conclusion we're drawing now, and maybe this isn't research you're doing, but maybe research others are doing, is there a way to try and figure out why the frequency has changed over time and what some of these other factors might be playing a role besides sea surface temperatures?
Some of the work that I'm doing and my colleagues doing and other lab groups around the world are working on right now is also kind of at some of these same locations, reconstructing changes in things like rainfall and drought patterns. Because oftentimes a lot of the atmospheric features that can cause storms to be steered in one direction versus another, or can kind of inhibit or enhance the formation of storms, is also very connected to rainfall. And by looking at rainfall changes and seeing how that's changing alongside hurricane activity in a region, we can also start to understand, okay, so we know this atmospheric feature impacts rainfall. It may also impact storms. And based on these changes in rainfall, it was like this at that time. So we can kind of start to, take these steps and look at broader climate changes and over these timescales, and then try to connect that to the storm activity. So we do have some hypotheses that we're still exploring. And I think for the what we've kind of been working on now is just getting a handle on where and how it's changing and what that looks like at a regional scale. And that's kind of the next step in what we're hoping for, kind of the next 10 years of our research is to really start nailing down, okay, what are the specific climate features and atmospheric features that are causing some of these changes that we're observing.
Tyler, this stuff is so fascinating. The paleo reconstructions using the physical data, using numerical simulations, and trying to get a better understanding on where our environment has been and what that means for us in the future, I think is so important going forward as we make decisions, as we plan where we're going in the next 50 to 100 years. So very much appreciate the work you're doing up there in Woods Hole. So let me ask you, where can people find out more about your work online, et cetera, et cetera?
Yeah, absolutely. So I actually just wrote a piece for the conversation that I can share with you if you wanted to link that. That's a great kind of breakdown of what we do. I can also link our lab's website, and that shows kind of where we're working around the world and some of the projects that we're involved in. We're actually also creating a kind of map viewer so you can see where we have paleo hurricane data from, and you can actually, anyone can access that and look at it for themselves to kind of see what's going on there. So that's going to be coming onto our lab website very soon. I also just gave a TEDx talk over some of this work, and that's something that you can keep your eye out for down the road. It's at the TEDx Boston Planetary Stewardship event, really just trying to get out and share about how we can better anticipate regional hurricane risk using these kind of non-traditional, unique records.
That's great stuff. Are you on social media at all? Or are you kind of back away from that in this day and age?
I do have an Instagram that I share some pictures from the field on. So my Instagram is stormy_oceanographer. So I post a lot of pictures from the field and kind of get some insight into this work and how we're doing it. And so that's kind of where I like to, update on that front.
That all sounds fantastic, Tyler. Again, thank you so much for joining us, and keep us posted on everything that's going on there for you and your team up in Woods Hole. We'll be right back in a moment with some closing thoughts on our Across the Sky podcast. And we're back with some closing thoughts on our Across the Sky podcast with Matt Holliner in Chicago and Kirsten Lang in Tulsa, Oklahoma. Our pal Joe Martucci's taking a little leave down in Florida this week. But I tell you, it's one of these things that I think we're kind of on the frontiers of in science. Matt, you and I were talking a little bit about this earlier. So often we say, oh, this only goes back to this satellite record, or this only goes back this far, or this only goes back but so far. The opportunity to go into some of these reconstructions, looking at some of these, whether it's ice cores in paleoclimatology, sediment cores, to kind of reconstruct what the climate has done in the more distant past has a lot of value.
Oh, absolutely. That's one of the questions I get oftentimes, because oftentimes when I'm talking about the records someplace, about like the hottest temperature, the coldest temperature, the record amount of rain, we're doing great if we can go back into the 1800s, because there are a lot of places where we don't even have that. But now we're talking about going hundreds of years back, even thousands of years back. And that's just amazing to me to be able to get that kind of information, because it's something we are so lacking. So any kind of method that we can get to look back at weather history, and in this case, hurricanes, but the more weather information we can get from the ancient past is great. Because yes, as meteorologists, we would like to look back farther, because obviously that comes into the question of climate change. It was like, okay, well, we know what happened a couple hundred years ago, but what about farther back than that? So anything like this, they can give us a clue about what was happening longer back before weather records were kept reliably is just absolutely fantastic.
Yeah, and I want to add this in too. I thought this was funny when we were asking about how long it takes for one of these samples, the process from the beginning to the end. People that aren't watching us and just listening, I was laughing because he was like, yeah, it takes about a month, you're out there. And then once you get it back, it takes 2 to 3 years. And I looked at all of our boxes and all three of us were like, whoa. I think that was kind of, the process of all of it. It's, I guess I didn't realize it. Obviously y'all didn't either, how long, that takes. That's pretty remarkable. I guess it makes sense, that it takes that long, but I think, you think of something like this and you're like, oh, maybe like 6 months, like half a year. And then when he's like, yeah, 2 to 3 years. So in total, like 3 to 5, it's a lot of research. It's a lot of time behind that, but very cool stuff. It's awesome listening to him. I don't think the three of us can say that enough.
Yeah, I have to imagine it's so intricate. You've got to get the physical stuff. You've got to take care of it. Then you've got to catalog it. Then you've got to find the right way to date it before messing it up. And then you have to do the correlations. And then you have to do the calibrations. Then you have to run this chemical signature against this. What is this telling me about what happened at this time? And then you have to do it for all of these different cores in different locations. I can absolutely get why it takes so long, for sure.
But it tells me that they're being really thorough with it, and doing it the right way, because I mean, that's the way to make sure that this technique that they're using is working, to look at in more recent times, how do these layers line up with the hurricanes that we saw, and trying to figure out like the intensity of the hurricane. When we know where a hurricane made landfall and how intense it was, then to be able to see, okay, that's what a core sample looks like when a Category 3 hurricane moves directly over this place. And then to compare that to when one hit maybe 50 miles away, what does that sample look like? So I imagine that there's just so much involved with this, but they seem to be putting the time to do it so they can get as much information out of these core samples. And it's just, amazing to me. We do it with the ice cores too, how much information we can gather from just looking at a pile of dirt, what it looks like to most of us. But there's clearly way more there. There's a lot more in the details there than what meets the eye.
It's funny, people say, well, what do geologists do? They look at rocks. Well, this is kind of the same thing. It's just kind of like water geology. There are messages, there are stories in the earth. You just have to know how to look for them and where to look for them. So he's got some great work, and looking forward to the work he's got ahead of him. Speaking of things ahead of him, before we close, we've got a couple cool shows in the offings here. We're going to be talking to one of our pals up in Alaska, Brian Bretschneider, in the coming couple of weeks. So he is all things Alaska weather, and we're going to talk to him about what's winter really like in Alaska. I'm really looking forward to talking with him. And also, we've got a couple other folks in the lineup. Greg Carbon, an old colleague of ours at the Weather Prediction Center in DC. Every year he talks about his favorite 10 or the top 10 weather events, maybe not necessarily favorite ones, but at least top 10 weather events. And he's going to be joining us a little bit later on in December as well. So some good stuff up ahead in the coming few weeks. But for now, I'm meteorologist Sean Sublett for my colleagues Matt Holliner in Chicago and Kirsten Lang in Tulsa, Oklahoma, and our pal Joe Martucci just running around Central Florida this week. Have a great week, and we'll see you next time on the Across the Sky podcast.